Hi everyone, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to go back to galaxies again in this video, but I want to actually cover probably three of the key structural indices or parameters that we can use to help classify galaxies. It's more of a mathematical way of classifying galaxies, help understand their formation and their evolution, because we have lots and lots of different sorts of galaxies. This could be a useful tool to help identify which is which, their past, their history, stuff like that. So if you're not familiar with galaxies, just a super quick recap on them really. So galaxies are these vast systems of stars, gas, dust, dark matter, and they're held together by gravity. Now, depending on the type of galaxy that it is, they're going to have different ratios of all those different things. So for example, elliptical galaxies have very little gas, they have older stars, different amounts of dark matter, that sort of thing. And galaxies as a whole come in a variety of different sizes and shapes. You've got your disk galaxies, you've got your elliptical galaxies, irregular galaxies, anything like that. And if we go to the actual Hubble classification system, so this is sometimes referred to as the Hubble tuning fork, because it's got a few different names. But on the right hand side you have your spiral galaxies. They evolve from right to left. The spiral arms get tighter, they lose gas content as they form into stars. Again, this is not the main point of this particular video, it's just a recap really. And then on your left hand side you've got your elliptical galaxies. These are featureless, they don't have spiral arms, they're essentially more spherical or elliptical, and they're just defined by their shape really. And it might be that they're all similar sort of shape, just how we're looking at them. But again, not the key part of this particular video. So most galaxies, in fact the vast majority of galaxies, they're not just on their own in space. Whilst there are these large collections of stars and other matter and stuff like that, they themselves group together. So they are quite often in these large clusters or these groups. You do get some that are more isolated, but the vast majority of them kind of clump together in these sort of groups. And you've got a good example there really. So you've got a galaxy cluster, also groups, and again I've done a separate video that explains what a group is, what a cluster is, and a small collection of galaxies is a group. A larger one, 1,000 galaxies or so, is going to be more of a cluster. Now the important thing in these particular sorts of structures as they clump together is that they interact with each other. These are big structures, they have a lot of gravitational interaction on each other, they move around, they're not static, and they can essentially influence their formation, their evolution, and how they actually evolve in these things. So if they're in a very dense environment, then they're going to collide more basically. If they're not, you're going to have less collisions between galaxies or interactions because they're more spaced out. So it's very important for understanding the evolution and even the formation process of galaxies themselves. So on to the three main structural indices. What are they used for? What's the purpose of them? Well, they're used to classify galaxies. Now we can visually classify galaxies. A spiral galaxy is fairly obvious. We can do spectroscopy, that sort of stuff. But this is another tool, or a set of tools really, for classifying galaxies. It'll help us understand their formation and evolution as well, because certain things are going to highlight maybe star formation, maybe mergers or distortion, that sort of thing. And it can also, we can apply these to large data sets as well. Because it's a mathematical tool, we've got a large data set, we can essentially let it work its magic through, not magic, but it can work through these very large data sets, which we now have for galaxies. They're quite large, some of these galaxy data sets that we have from these survey telescopes. And also, we can link the morphology of the galaxy to its physical and environmental process. What does that mean? Well, again, it goes back to those clusters really, and the fact that those galaxies are interacting, they might merge, they can tidally distort each other, so we can link how they look, their structural indices, parameters, to their physical environment and the processes that are occurring there. So the problem is most galaxies are not really nearby. They're quite a long way. And if you look really carefully on this, it depends what you're looking on. If you're looking on your phone, you probably can't see anything, they just look like stars. But there are some galaxies here, and they're quite faint, they're a long way off, and they're more of a blur. So how do I know that's a spiral galaxy, an elliptical galaxy? Is it distorted? Is it symmetric? So when they're very far away, it's very difficult to understand what type of galaxy that it is. So this is where the structural indices are going to come into play and help us there. If they're nearby, so this is one of our nearby galaxies, then it's pretty easy to classify galaxies or understand the processes which has led to their formation, how they're going to evolve. This is very clearly a spiral galaxy, a disk-like galaxy, but if it was a lot further away, we might not see that structure. So again, structural indices, very important for helping us identify if this is a spiral or not. So the very first one is the asymmetry parameter. Now this is looking at how symmetric the galaxy's light is if you rotate the image or the galaxy by 180. So on the left hand side we've got our original image taken. In the middle we've got the image rotated by 180, and then on the right hand side is essentially the difference between those two images. Now if it's symmetric, there shouldn't be any difference, but if it's asymmetric, we're going to get a new picture basically showing the asymmetry in it. So just to kind of highlight really, original image, rotated image, and then the asymmetry in the background noise. Now mathematically we've got our equation there, so you're just looking for the differences really between the two images that we've rotated 180, and we get this parameter, this asymmetry parameter A. So we get a value for that. If it's a low value, it means the galaxy is smooth, the light profile's symmetric, and this is fairly typical if you've got an undisturbed spiral or an elliptical galaxy. So a galaxy that hasn't had any interaction with another galaxy should be relatively symmetric. And if we have a high A, so a high asymmetry parameter, it's likely telling us that this galaxy is disturbed. It's either had a merge with another galaxy, or it's tidally interacting with another one which is distorting it, and it's pulling it away from that normal symmetric profile that it would have. So it's pretty useful for identifying galaxy mergers or interactions at much further distances really. So if we can't actually see these, we've got some galaxy mergers occurring there. If we can't see that occurring, this structural indice or parameter will help us identify if that is ongoing or not. Now our second one is the clumpiness parameter, and this is measuring how patchy the galaxy light is, and it will highlight small scale structures, most likely where you've got star forming regions. So star forming regions are going to be brighter than the surrounding galaxy, and these will be smaller scale structures. So again, we've got our original image on the left. In the middle we've actually applied some kind of filter to that, some smoothing filter, and then we're looking for the difference between the two, and that gives us this clumpiness parameter. So there you go, you've got your original image, you've got one that's been smoothed with kind of like a filter or kernel. An example might be a Gaussian one, and then you've got the clumpiness of the background noise, so are kind of the differences that you're getting between the two. And mathematically it's this equation here. So you get this clumpiness parameter S. Now if we have a low S number, you've got a smooth light profile again. It means the galaxy is quite quiet. There's little to no star formation, so we don't have any pockets of star formation occurring in there. So it's fairly quiet. Could be an older galaxy where the star formation has dropped off. You typically get star formation occurring in younger galaxies. And if we have a high S value, then it means the galaxy is clumpy, it's got an irregular structure, and it's likely got active star formation occurring in it. So this one can help us identify things like star formation rates. This could identify whereabouts on its evolutionary path it might be. And then our final one is the concentration parameter. Now this is going to measure how much of the galaxy's light is in the core of it versus the edge of the galaxy. So is it brighter in the center or not? So here we've got two circles that we draw around the galaxy, and the first one is this R20. That is the radius that contains 20% of the total light of the galaxy, and then you've got your R80, which is the radius that contains 80% of the total light. Now what we're doing here mathematically is, again, we're just looking for how evenly distributed that light is from the centre to the outer part. Now if you've got a low C, a low concentration parameter, then the light is more evenly spread throughout the galaxy. So as we get from the centre to the outer part, there's not a huge difference in how bright it, or the drop in the brightness basically. And this could be indicative of like a disk galaxy, a spiral galaxy, irregular galaxy maybe. But if we've got a high concentration parameter, then the light is tightly packed in the centre. And this would be fairly typical for an elliptical type galaxy, or one that has a fairly significant bulge in it. Now bulges typically grow as galaxies age, so again it could be another indicator of the evolutionary process of a galaxy. So going back to this first bit, galaxies come in a variety of sizes and shapes, and applying these tools, these parameters, can help us identify when they are much further away and we don't get a clear view of the galaxy themselves. So it's a very useful tool to be using. So they can reveal the structure, star formation activity, and its evolutionary stage, even if we can't see it properly. So thank you for watching. If you enjoy the videos, then consider becoming a member of the channel. There's extra videos in the members section, but it also helps support the channel. So thank you for watching.